Section 8.2, Reactive Servers with Spring WebFlux and Spring Data R2DBC. So far we have worked on Catalog Service, a non-reactive, or imperative, application, using Spring MVC and Spring Data JDBC. This section will teach you how to build a reactive web application, order service, using Spring WebFlux and Spring Data R2DBC. Order service will provide functionality for purchasing books. Like Catalog Service, it will expose a REST API and store data in a PostgreSQL database. Unlike Catalog Service, it will use the reactive programming paradigm to improve scalability, resilience, and cost-effectiveness. You'll see that the principles and patterns you learned in the previous chapters also apply to reactive applications. The main difference is that we'll shift from implementing the business logic in an imperative way to building reactive streams that are processed asynchronously. Order service will also interact with Catalog Service through its REST API to fetch details about books and check their availability. That will be the focus of Section 8.3. Figure 8.4 shows the new components of the system.
Figure 8.4. The order service application exposes an API to submit and retrieve book orders, uses a PostgreSQL database to store data, and communicates with book service to fetch book details.
As you learned in Chapter 3, we should start with the API first. Order service will expose a REST API to retrieve existing book orders and submit new ones. Each order can be related to one book only and up to 5 copies. The API is described in Table 8.1.
Table 8.1. Specifications for the REST API that order service will expose. View table figure.
Now on to the code. Note: if you haven't followed along with the examples implemented in the previous chapters, you can refer to the repository accompanying the book and use the project in the Chapter 08/08 Begin folder as a starting point. See this link. Section 8.2.1. Bootstrapping a reactive application with Spring Boot. You can initialize the order service project from Spring Initializer, start.spring.io, store the result in a new order service Git repository, and push it to GitHub. The parameters for the initialization are shown in Figure 8.5.
Figure 8.5. The parameters for initializing the order service project from Spring Initializer.
Tip: if you don't want to go through the manual generation on the Spring Initializer website, you'll find a curl command in the Begin folder for this chapter that you can run in a terminal window to download a zip file. It contains all the code you'll need to get started. The dependencies section of the auto-generated build.gradle file is shown here.
See this code?
These are the main dependencies. Spring Reactive Web, org.springframework.boot, Spring Boot Starter WebFlux, provides the necessary libraries for building reactive web applications with Spring WebFlux and includes Netty as the default embedded server. Spring Data, R2DBC, org.springframework.boot, Spring Boot Starter Data, R2DBC, provides the necessary libraries to persist data in relational databases with R2DBC using Spring Data in reactive applications. Validation, org.springframework.boot, Spring Boot Starter Validation, provides the necessary libraries for object validation using the Java Bean Validation API. PostgreSQL, org.postgresql R2DBC PostgreSQL, provides an R2DBC driver that allows the application to connect to a PostgreSQL database reactively. Spring Boot Test, org.springframework.boot, Spring Boot Starter Test, provides several libraries and utilities to test applications, including Spring Test, JUnit, AssertJ, and Mockito. It's automatically included in every Spring Boot project. Reactor Test, io.projectReactor Reactor Test, provides utilities to test reactive applications based on Project Reactor. It's automatically included in every reactive Spring Boot project. Test Containers, org.testcontainers, JUnit Jupyter, org.testcontainers, PostgreSQL, org.testcontainers, R2DBC, provides the necessary libraries for testing applications using lightweight Docker containers. In particular, it provides test containers for PostgreSQL supporting the R2DBC driver. The default and recommended embedded server for reactive applications in Spring Boot is Reactor Netty, which is built on top of Netty to provide reactive capabilities within Project Reactor. You can configure it either through Properties or by defining a Web Server Factory customizer of Netty Reactive Web Server Factory component. Let's use the first approach. First of all, rename the application.properties file generated by Spring Initializer to application.yml and define the application name using the spring.application.name property. Like you did for Tomcat, you can define the server port through the server.port property, configure the graceful shutdown through server.shutdown, and set the grace period with spring.lifecycle.timeout per shutdown phase. Using the specific Netty properties, you can further customize the server's behavior. For example, you can define connection and idle timeouts for Netty with the server.netty, connection timeout, and server.netty.idle timeout properties.
Listing 8.1. Configuring Netty server and graceful shutdown.
With this basic setup in place, we can now define the domain entity and its persistence. Section 8.2.2. Persisting data reactively with Spring Data R2DBC. In Chapter 5, you learned that interactions between a Spring Boot application and a database involve database drivers, entities, and repositories. The same concepts you learned in the context of Spring Data JDBC also apply to Spring Data R2DBC. Spring Data provides common abstractions and patterns, making it straightforward to navigate the different modules. The main difference for order service compared to catalog service is the type of database driver. JDBC is the most common driver used by Java applications to communicate with a relational database, but it doesn't support reactive programming. There have been a few attempts to provide reactive access to a relational database. One project that stood out and that is widely supported is Reactive Relational Database Connectivity, R2DBC, initiated by Pivotal, now VMware Tanzu. R2DBC drivers are available for all the major databases, such as PostgreSQL, MariaDB, MySQL, SQL Server, and Oracle DB, and there are clients for several projects, including Spring Boot with Spring Data, R2DBC, and test containers. This section will guide you through defining a domain entity and a persistence layer for order service using Spring Data, R2DBC, and PostgreSQL. Let's get started. Run a PostgreSQL database for order service. First of all, we need a database. We'll adopt a database per service approach to keep our applications loosely coupled. Having decided that catalog service and order service will have a database each, we have two options for the actual storage. We could either use the same database server for both databases or two different ones. For convenience, we'll use the same PostgreSQL server we set up in Chapter 5 to host both the PolarDB_catalog database used by catalog service and the new PolarDB_order database used by order service. Go to your Polar deployment repository and create a new Docker PostgreSQL folder. Then add a new init.sql file in the folder. Add the following code to the init.sql file. It is the initialization script that PostgreSQL should run during the startup phase.
Listing 8.2. Initializing the PostgreSQL server with two databases.
Next, open the Docker compose.yml file and update the PostgreSQL container definition to load the initialization script. Remember to remove the value for the PostgreSDB environment variable, since we'll now delegate the database creation to the script. In the book's source code, refer to Chapter 08/08n/polardeployment/docker to check the final result.
Listing 8.3. Initializing the PostgreSQL server from an SQL script.
Finally, start a new PostgreSQL container based on the new configuration. Open a terminal window, navigate to the folder where you defined the docker compose.yaml file and run the following command.
See this code?
For the rest of the chapter, I will assume you have the database up and running. Connecting to a database with R2DBC. Spring Boot lets you configure the integration of a reactive application with a relational database through the Spring R2DBC properties. Open the application.yml file for the order service project and configure the connection with PostgreSQL. Connection pooling is enabled by default, and you can further configure it by defining connection timeout and sizes, just like you did for JDBC in Chapter 5. Since it's a reactive application, The connection pool will probably be smaller than when using JDBC. You can tune the values after monitoring your applications running under normal conditions.
Listing 8.4. Configuring the database integration over R2DBC.
Now that you have connected a Reactive Spring Boot application to a PostgreSQL database through an R2DBC driver, you can go ahead and define the data you want to persist. Defining persistent entities. The order service application provides functionality for submitting and retrieving orders. That's the domain entity. Add a new com.polarbookshop.orderservice.order domain package for the business logic and create an order Java record to represent the domain entity, much like you defined book and catalog service. Following the same approach used in Chapter 5, use the ID annotation to mark the field representing the primary key in the database, and use version to provide a version number, which is essential for handling concurrent updates and using optimistic locking. You can also add the necessary fields to hold audit metadata using the created date and last modified date annotations. The default strategy for mapping an entity to a relational table is to transform the Java object name into lowercase. In this example, Spring Data would try to map the order record to an order table. The problem is that order is a reserved word in SQL. It's not recommended that you use it as a table name because it would require special handling. You can overcome that issue by naming the table orders and configuring the object relational mapping through the table annotation from the org.springframework.data.relational.core.mapping package.
Listing 8.5. The order record defines the domain and persistent entity.
Orders can go through different phases. If the requested book is available in the catalog, then the order is accepted. If not, it's rejected. Once the order is accepted, it can be dispatched, as you'll see in Chapter 10. You can define these three statuses in an order status enum in the com.polarbookshop.orderservice.order.domain package.
Listing 8.6. Enum describing the statuses for the orders.
The R2DBC auditing functionality can be enabled in a configuration class using the enabler2dbc auditing annotation. Create a data config class in a new com.polarbookshop.orderservice.config package and enable auditing there.
Listing 8.7. Enabling R2DBC auditing via annotation configuration.
Having defined the data you want to persist, you can go ahead and explore how to access it. Using reactive repositories. Spring Data provides the repository abstraction for all the modules in the project, including R2DBC. The only difference between this and what you did in Chapter 5 is that you're going to use a reactive repository. In the com.polarbookshop.orderservice.order.domain package, create a new order repository interface and make it extend Reactive CRUD repository, specifying the type of data handled, order, and the data type of the ID annotated field, long.
Listing 8.8. Repository interface for accessing orders.
The CRUD operations provided by Reactive CRUD repository are enough for the use cases of the order service application, so you won't need to add any custom methods. However, we're still missing the orders table in the database. Let's define it using Flyway. Managing database schemas with Flyway. Spring Data R2DBC supports initializing data sources through schema.sql and data.sql files, just like Spring Data JDBC. As you learned in Chapter 5, that functionality is convenient for demos and experiments, but it's better to manage schemas explicitly for production use cases. For catalog service, we used Flyway to create and evolve its database schemas. We can do the same for order service. However, Flyway doesn't support R2DBC yet, so we need to provide a JDBC driver to communicate with the database. The Flyway migration tasks are only run at application startup and in a single thread, so using a non-reactive communication approach for this one case doesn't impact the overall application scalability and efficiency. In the build.gradle file for your order service project, add new dependencies to Flyway, the PostgreSQL JDBC driver, and Spring JDBC. Remember to refresh or re-import the Gradle dependencies after the new addition.
Listing 8.9. Adding a dependency for Flyway and JDBC in order service.
Then you can write the SQL script for creating the orders table in a v1 double_initial_ schema.school file under src/main/resources/db/migration. Ensure you type 2 underscores after the version number.
Listing 8.10, Flyway Migration Script for Schema Initialization.
Finally, open the application.yml file and configure Flyway to use the same database managed with Spring Data R2DBC, but using the JDBC driver.
Listing 8.11, Configuring the Flyway integration over JDBC.
As you probably noticed, defining domain objects and adding a persistence layer in a reactive application is similar to what you would do with imperative applications. The main differences you encountered in this session are using the R2DBC driver instead of JDBC and having a separate Flyway configuration, at least until R2DBC support is added to the Flyway project. See this link. In the next section, you'll learn how to use Mono and Flux in your business logic. Section 8.2.3, Implementing the business logic with reactive streams. The Spring Reactive stack makes it straightforward to build asynchronous, non-blocking applications. In the previous section, we used Spring Data R2DBC and didn't have to deal with any underlying reactive concerns. That's generally true for all the reactive modules in Spring. As a developer, you can rely on a familiar, simple, and productive approach for building reactive applications, while the framework takes care of all the heavy lifting. By default, Spring WebFlux assumes that everything is reactive. This assumption means that you're expected to interact with the framework by exchanging publisher of T objects like mono of T and flux of T. For example, the order repository we created earlier will give access to orders as mono of order and flux of order objects instead of returning optional of order and collection of order like it would do in a non-reactive context. Let's see that in action. In the com.polarbookshop.orderservice.order.domain package, create a new order service class. For starters, let's implement the logic to read orders through the repository. When multiple orders are involved, you can use a flux of order object, representing an asynchronous sequence of 0 or more orders.
Listing 8.12, Fetching orders via a reactive stream.
Next, we need a method to submit orders. Until we have the integration with catalog service in place, we can always default to rejecting submitted orders. Order repository exposes a save method provided by Reactive CRUD repository. You can build a reactive stream to pass an object of type mono of order to order repository that will save the order in the database. Given an ISBN identifying a book and the number of copies to order, you can build a mono object with mono.just, in the same way you would build a Java stream object with stream.of. The difference is in the reactive behavior. You can use the mono object to start a reactive stream and then rely on the flatmap operator to pass the data to order repository. Add the following code to the order service class and complete the business logic implementation.
Listing 8.13, Persisting rejected orders upon submitting order requests.
Map versus flatmap. When using Reactor, choosing between the map and flatmap operators is usually a source of confusion. Both operators return a reactive stream, either mono of T or flux of T, but while map maps between two standard Java types, flatmap maps from a Java type to another reactive stream. In listing 8.13, we map from an object of type order to a mono of order, which is returned by order repository. Since the map operator expects the target type not to be a reactive stream, it will wrap it in one nevertheless and return a mono of order object. On the other hand, the flatmap operator expects the target type to be a reactive stream, so it knows how to handle the publisher produced by order repository and returns a mono of order object correctly. In the next section, you'll complete the basic implementation of order service by exposing an API to fetch and submit orders. Section 8.2.4, Exposing a REST API with Spring WebFlux. There are two options for defining RESTful endpoints in a Spring WebFlux application: REST controller classes or functional beans, router functions. For the order service application, we'll use the first option. Unlike what we did in Chapter 3, the method handlers will return reactive objects. For the GET endpoint, we can use the order domain entity we defined earlier and return a flux of order object. When submitting an order, the user must provide the ISBN of the desired book and the number of copies they would like to purchase. We can model that information in an order request record that will act as a data transfer object, DTO. It's also good practice to validate the input, as you learned in Chapter 3. Create a new com.polarbookshop.orderservice.order.web package and define an order request record to hold the submitted order information.
Listing 8.14. The order request DTO class with validation constraints.
In the same package, create an order controller class to define the two RESTful endpoints exposed by the order service application. Since you defined validation constraints for the order request object, you also need to use the familiar valid annotation to trigger the validation when the method is called.
Listing 8.15. Defining handlers to process REST requests.
This REST controller completes our basic implementation of the order service application. Let's see it in action. First, make sure the PostgreSQL container you created earlier is still running. Then, open a terminal window, navigate to the order service project's root folder, and run the application.
See this code?
You can try out the API by submitting an order. The application will save the order as rejected and return a 200 response to the client.
See this code?
To make it possible to submit orders successfully, we'll need to make order service call catalog service to check the book's availability and fetch the necessary information for processing the order. That's the focus of the next section. Before moving on, stop the application with Ctrl+C.